When we take measurements with a digital computer, we will record the signal values at discrete times. In between those sampling times, we have no information about the signal. This necessitates taking precautions whenever we make measurements so that we can get a valid reconstruction of the original signal. These precautions mean restrictions on the signal and the sampling rate, and we'll look at that whenever we talk later about data acquisition. For now, we're going to look at the Fourier transform, which determines the frequency components of a time-varying signal. The reason this is useful for us is if we know the frequency components of the signal, then we can use that to help us determine our instrumentation needs, the transducer dynamic characteristics, and also the sampling rate, the speed at which we sample the data, and filtering, what kind of filtering is going to be used. When we talk about the Fourier transform, we use it because we want to find the frequency components of a signal. In other words, how strong is any given frequency in an arbitrary signal. What we're going to examine in this video are the steps for getting this information. We'll start with the Fourier series, which says that any periodic function can be written as an infinite sum of sinusoids. And these sinusoids are at frequencies of integer multiples of the base frequency. Base frequency being the frequency of this periodic function. And if we have a non-periodic signal, we can copy them to make them periodic. So the Fourier transform is what we use to go from a continuous signal, this arbitrary signal, into a series of sinusoids. It'll give us a summation. Well, it'll convert the Fourier series into an integral. And this is what allows us to evaluate the content at any given frequency. However, it's not very useful whenever we have discrete data, and so we'll finish up the video by looking at the discrete Fourier transform. Whenever we use the Fourier transform on a computer, it typically uses a special algorithm called the fast Fourier transform, and that speeds up the calculations for the Fourier transform. Again, we're going to examine the Fourier series, the Fourier transform, and then the discrete Fourier transform. Here we have a periodic function, which is our signal, and it has a period t, which gives us 2 pi over omega naught. So omega naught would be our base frequency. And we can represent this as an infinite sum, where we have a constant term, a0, and then an infinite sum of cosine functions, where they have magnitude a1, a2, all the way up to an, and frequencies omega naught, 2 omega naught, all the way up to n times omega naught. Adding to that, we have an infinite sum of sine functions, where they have magnitudes b1, b2 through bn, and frequencies omega naught, 2 times omega naught, all the way up to n times omega naught. The Fourier series has coefficients given by these equations, these integrals. So a0 we can find from this integral. The an coefficients are given here, and then the bn coefficients are given in this equation. So we could write this as an infinite summation according to this equation. So how do we get those coefficients? We're going to look at where they came from, or those equations for finding the coefficients. First, we'll derive the equation for the a naught coefficient, this one. To do that, we want to integrate both sides of the equation from 0 to t. So that's what that looks like. And when we evaluate these integrals, we find that we have a0 times t, evaluated from 0 to t, and then a constant times sine n omega naught t from 0 to t, and then another constant times cosine n omega naught t. But if we look at the frequency, which is 1 over the period, so this f is not the same as this f. This is our signal function, and this is the frequency. And that's equal to omega naught over 2 pi. Now, that gives us that omega naught times t is equal to 2 pi. So whenever we're doing these evaluations, we have we're looking at sine of 2 pi minus sine of 0. So the integral of cosine from 0 to 2 pi, and that integral is 0. And here we have the integral of sine from 0 to 2 pi, so that's 0 also. What we're left with then is a naught times period t. And that's where we get the equation that a naught is 1 over t times the integral from 0 to t of f dt. Now we can do a similar process for the next coefficients, except this time we're going to multiply both sides of the equation by sine m omega naught t, and then we'll take the integral from 0 to t. That's what we have here, and this term is similar to what we had up here. We're evaluating this integral of sine m omega naught t from 0 to 2 pi, because remember the product of t and omega naught is 2 pi. So 0 to 2 pi. So this integral is going to be 0. And here we have cosine times sine from 0 to 2 pi, which is also 0. This last term, sine n omega naught t times sine m omega naught t. Whenever n and m are not equal, that evaluates to 0. That integral is 0. But whenever n and m are equal, then it becomes sine squared of n omega naught t. That integral looks like this, and if we evaluate that from 0 to t, then this constant term goes away, and we're left with 1/2 b sub n times t. And that gives us the equation for the sine coefficients, b sub n. We could do a similar process where we multiply both sides by cosine m omega naught t and take the integral, and that would give us the equation for a sub n, the coefficients for the cosine functions. Now we can rewrite this series in exponential form, because the sum of the cosine and sine functions can be rewritten as a complex exponential. So these are equivalent expressions. It's just this is the complex exponential form. And here's the expression for the coefficient c sub n. Now that we've looked at the Fourier series, we're going to examine the Fourier transform. And that's useful for evaluating non-periodic signals. Here's the Fourier series in complex exponential form, and we're just going to rewrite the coefficients in terms of omega naught instead of in terms of the period. If we had this signal where we measure it over this period, t, what's the base frequency omega naught of this signal? Well, it's just 2 pi over this time period. And so we can make this periodic by copying it like that. And we also want to find what the contribution of each frequency is to the original signal. So we're going to look at the Fourier transform. First of all, again, here's the Fourier series in complex exponential form. First of all, we're going to start with some function g, which depends on omega. And we'll consider it to be a discrete function. So here at omega naught, g has one value. At 2 times omega naught, it has another value. 3 times omega naught, it has another value. If we were to sum the values of g times n omega naught for n equals 1 to 4, we would just be adding up the values of g, and it looks like this. And then if we multiplied that by omega naught, it would give us the area under this curve. If omega naught becomes very small, so these rectangles become quite skinny, in fact, as omega naught approaches 0, this summation would be equal to the integral of g of omega times d omega. So we're going to look at the Fourier series and this Cn times exponential j n omega naught t is our function g omega. So we want to apply this relationship to the Fourier series. So we now have an integral instead of this infinite sum. And we're going to use the same, we're going to plug in our expression for c sub n here, and we're taking the limit as omega naught goes to 0. And so we end up with this expression for our Fourier series. Now we can just distribute the constant terms, and we have this double integral, and we end up with an expression for the Fourier transform. So this capital F of omega is the strength of the signal at frequency omega. This is the Fourier transform for a signal f of t. And if we know the strength of all the frequencies, or strength of the signal at all the frequencies, so if we know capital F, then we can use the inverse Fourier transform to reconstruct the original signal. And this is for continuous values of omega, so an infinite range of values for omega. But as stated earlier, whenever we take data with a digital computer, we want to work in the discrete domain instead of continuous values. Here again are the Fourier transform and the inverse Fourier transform, rewriting those in terms of f instead of omega. We have these expressions here. And now whenever we're talking about discrete data, let's look at that for a second. If we have a signal and we measure it for a time t, and we take 8 data points, then we have the parameters capital T is our signal length, n is our number of data points, and delta t is the time between samples. Now we have delta f is the base frequency, that's the smallest detectable frequency, and that's just 1 over our signal length. That's the smallest frequency that we're going to find the magnitude of, or the contribution of, in our discrete Fourier transform. And then the largest frequency, or the highest frequency that we'll find the contribution of, is given here. F max is n minus 1 times the base frequency. So here is the Fourier transform in discrete form. We have the original signal, but we're evaluating it at discrete time points. So n is integer values, and delta t is the time between each sample. So the value of our signal at these discrete points is given here, and this is the discrete Fourier transform. And this is what it looks like if we just renumber our indices starting with negative values, so going from negative 1/2 n up to positive 1/2 n minus 1. This is the expression for the discrete Fourier transform. If we have our sampled data, then we can find the contribution of integer multiples of our base frequency. So here k is an integer, and delta f is the base frequency. So we can find the contribution of integer multiples of our base frequency by evaluating this summation over all of our samples of our sampled data. Let's look at an example. Say we have an original signal that comprises these two sine functions. Here we have 2 times sine of 2 pi times 10t. So the frequency of this one is 10, and the frequency of this is 15. And this is what it looks like plotted in the time domain. We want to perform the discrete Fourier transform so that we can try to determine what are the contributions of different frequencies. So we're going to sample this over a period of 1 second, and we'll take 128 measurements during that time. This gives us that delta t is 7.87 milliseconds, and our base frequency is 1 hertz. The smallest frequency that we will look at the contribution of is 1 hertz, and then we'll examine the contribution of integer multiples of 1 hertz. So performing this discrete Fourier transform, we end up with contributions that look like this. So here we have the contribution of 15 hertz signal, and then we would expect, so there's that signal, and we would expect a 10 hertz signal to have a magnitude about twice the 15 hertz signal. So there's that one. From the original signal, we should like to see the contributions of any frequency other than 10 or 15 hertz being 0, but the discrete Fourier transform doesn't give us that because we have some appreciable value for delta t. It's not an exact reconstruction. If we think back to the material on the dynamic measurements, we can see that having the frequency components of a signal would be useful in order to pair that with the dynamic characteristics of a transducer in order to find a suitable transducer for a measurement system.